You know, it's like that. You bring your car to a mechanic who knows nothing, that says, "Oh, memorization is not good." You know, don't bother. But then again, memorization is a tremendous amount of work. But and I have a hard time memorizing things, but I found a way to memorize them pretty easily without too much work. And that is, if I had trouble memorizing something, I would just review it, every day. It doesn't take long to just read through your notes, so you can memorize a lot of information. But it also makes a big difference how much you write. Some people write nothing, and therefore they memorize very little, and therefore they have very little knowledge, and therefore you would consider them total novices, total beginners. And then there are other people who write down a lot of stuff and can memorize a lot of things, and then those would be the experts. In science, it's gonna go like this. This is the time to start, because this is the beginning. As you progress, what you're going to find is it's like a marathon. It's like a marathon where the top students get farther and farther away from you, and they're further and further ahead. But you're in the same class. You're supposed to be going at the same pace. This is what I meant by when I transferred to UCLA. It was like that. I wasn't prepared for that, and so all of a sudden the curve had shifted, and I didn't shift either along with it, and so I was still down here. Well, if the curve shifted and I was still down here, that's why my grades suffered the first quarter and a half, and then finally it changed. But the memorization, yes, it is a lot. Chemistry does have a lot of stuff to memorize, but it's very important that you do start to work on memorizing it. But how do you memorize it? You don't memorize it in one night. You have to memorize it over time. And I've seen lots of people try to memorize it in one night unsuccessfully. And even if you do memorize it in one night and pass the classes, then as you continue on, you just get further and further behind. I told you, I told you about my friend, right? The one who was preparing for medical school. That's that kind of situation. So, anyway, so now's the time to do it. We just started. I mean, how many days do we have? Monday, Tuesday, Wednesday, 3 days of information. 3 days of information, you should be able to memorize that without much difficulty, at least to build a base, to build a base. And so, as far as other separation techniques go, one easy one would be the one on the PowerPoint. What was the one on the PowerPoint? The magnet, so nobody mentioned the magnet. That would be easy points right there. Magnet, separating out. Not that mixture would be very common. That would be a very rare mixture, and that's kind of a weird technique, but hey, it's a separation technique. And that requires not like reverse osmosis where, you'd have to have other experiences to come up with reverse osmosis. Reverse osmosis is an excellent technique. However, our purified water here is not made by reverse osmosis, and it's not made by distillation. Distillation is too expensive. Reverse osmosis is too expensive. We use a much cheaper technique to purify it, but still it's expensive. It still costs maybe, our water, I calculated it the other day, it costs about 75 cents a gallon for this water here. And what we do is we have a special kind of chemical filtration technique where you pass it through a resin and it takes out the species, which we're going to talk about it. It's called ion exchange. But there are lots of techniques for separating out mixtures. One of the classic techniques that I might as well talk because this is a big one. A big one is called chromatography. Have you ever put a piece of paper in a water glass and the water creeps up the paper or climbs up the paper? Well, yeah, that happens because the water and paper like each other, and so the water will try to maximize its contact with the paper until gravity prevents it from going any higher. Well, we can take advantage of that because water likes paper, but there are other things that like paper too, and there are other things that don't like paper as much. And so the things that really like paper will spread out on the paper. The things that don't like it will stay clumped together. And so one of the classic techniques is using paper, and they call it paper chromatography, where they'll put the paper in some kind of a mixture and then let the components of the mixture climb up the paper. And so there are things that really like it and will climb really high, and things that don't, that won't climb up as high. And so for the classic examples, ink. You know, the inks that we have in pens, are they pure? It might be, but typically the inks here are mixtures. They're mixtures of different compounds. And most of them are different colors. And so they mix different colors ink to get the ink for your pen. Well, we can separate the ink into its different substances by letting it climb up the paper, like that. That's paper chromatography. But to take that one step higher, sometimes all the inks kind of like, and they all clump together. And so what we need is a much longer paper, but then things stop. So usually we don't use water, we use alcohol. Alcohol can climb up much higher, carry the inks up much higher. And so that would be paper chromatography, but we take it to the next level. Rather than using paper, there are certain resins that we can use that do the same thing. And then we, rather than using a short length of this, you use 100 feet of it. Now 100 feet would go 10 floors up. But we aren't going to do it this way. You're going to put the resin into a tube and make a long coil of this. And so you'll have 100 feet there. That way, if you have the longer distance marathon, then they can spread out more and more. And so the inks will give you a clean separation. And so that's called chromatography. That's another technique. There are a whole bunch of techniques that we can use to determine. And sometimes when we're here, how do we know? Is it pure or is it a mixture? If it looks homogeneous, how do we know whether it's pure or mixture? Okay, that's good. If you look at it at the microscopic level, you might see that it isn't. So, for example, if we took brass, or if we took sterling silver might be hard to see, but if we took brass, is a lot easier to see. If you magnify it, you'll see tiny crystals of copper, zinc, etc., all clumped together. And so it looks homogeneous with our eyes at the macroscopic level, but at the microscopic level it looks heterogeneous. Milk looks homogeneous, right, to our eyes, but at the microscopic level milk is quite heterogeneous. And so milk is a mixture. And so we could use a microscope. How else could we do that? Could we do that for a water sample? We use a microscope and see if we could see the impurities, and actually the microscope wouldn't be enough. We'd need something that would see it at what level? At the atomic molecular level, which is what we called the, what do we call it? The atomic molecular level. We called it, not subatomic. Things that are at the atomic or molecular level are at the particulate level. So if we look at it by individual particles, the individual particles, do they have to be molecules? No, they could be atoms as well. They could be atoms, molecules, or proteins are molecules. Proteins are gigantic molecules. Lattice. It could be at the lattice level, right? Atoms, molecules, or we talked about two types of lattices. What were they? Ionic and covalent lattices. Let me tell you one other thing that happened at UCLA. At UCLA, the exams are very long. The time is very short. So you got a long exam with too little time. You're not going to finish the exam. And so who are the people who are going to get the top scores? The people who are going to get the top scores are the people who are fast. Well, how do you become fast? Are they naturally fast? Or what? You know how they became fast is they just had a lot of information, in other words, the recall was very fast. And so rather than, and this is what I noticed, that like, if somebody asks the question, oh, this guy, he's on it all the time, he's always answering questions. Well, how did he get to that point where he's always answering questions all the time? Well, I found out, it's just recall. And how do you get the recall? It's not because he's a genius. He got the recall because he just goes over it and over it and over it. If you go over it, it starts to get boring. I'll tell you, by the 15th, 20th time you read the same thing over and over again, it gets a little bit boring because you have it down. You understand it, right? And you have it memorized. And so after doing this a bunch of times, then you start thinking. You want to go beyond it because it's getting a little tiring. This is like kindergarten. I want to go to the next step, And so you start thinking about the information in different ways. When you start thinking about the information in different ways, then you can really solve much more complex problems. But the people who don't even have this stuff down, they can't even solve a simple problem. They're the beginners. They're the ones you bring your car to the auto mechanic. They don't know what's going on just as much as you don't know. Or I'm not saying you don't know, but in case you don't know cars, just as much as you don't know. And so you want to have that. And so this is why, what I'm doing here is I'm seeing what is your level of recall. What your level of recall is well, one, you have to have the information down first. And two, you have to review it. And so do you review it before class? I used to review it before class, so it was fresh in my mind. And do you review it? How often do you review it? Maybe you have to review it more, maybe you have to review it less. But you just need to be able to recall information quickly. And then you go, well, that's just memorization. But if you have a good command of this, then you can solve a lot of problems. Now, I can't even recall what were we talking about.
We were talking about things like lattices, atoms, molecules.
Okay, lattices, yeah. Lattices. And so the two types of lattices was already mentioned, ionic and covalent. The difference between an ionic and covalent lattice, don't worry at this time. But that's what happens. Like after the 15th time or 20th time you read ionic and covalent lattices, you get kind of frustrated. Well, I might as well punch it out, Google it or something, or Wikipedia, see what an ionic lattice or covalent lattice is. It's one of those things left hanging, not complete. But you don't get there, and that's how that's how people get so much farther ahead in class. And then what tends to happen is the grade distribution gets totally screwed up. You have the people who are way far ahead, and then a lot of people who are way far behind. And it just happens. It starts to happen. But we're all bunched up. We're all bunched up right at the beginning of this marathon of college. And so it's kind of like even right now. But as that marathon, but now we're running. And so are you going to be in the lead pack or are you going to be in the straggler pack? This is what you can determine right now. Do you want to be in the lead pack or the straggler pack? If you want to be in the lead pack, then the leaders there are already way ahead. When I had transferred there, that guy knew so much more basic knowledge than I did. And therefore he was able to solve a lot of questions. And so I ended up having to go back into my in fact, when I went there, because I had already taken general chemistry, I went to the bookstore and bought the general chemistry book that they used at UCLA. The general chemistry book that they used at UCLA was like an order of magnitude harder than the one I had used when I was at Santa Barbara City. And so I did that so I could play catch up. But playing catch up is not fun. It's a waste of time. You don't have to do it because you're still going to be behind. I felt perpetually behind. I was like in the straggling crowd trying to catch up with the lead pack. It was hard. But eventually, eventually I caught up. And then it was okay. But if I just started from the beginning, it would have been easy. Just like if that guy had started studying for the MCAT at the beginning, this guy had wanted to go to medical school for years. And I have no idea why he didn't start studying earlier. And he just waited until the last minute to start preparing for the MCAT, which is the most important thing. But you know what? He finally did make it into medical school. He went to the American Medical School in the Caribbean, which in the Caribbean they don't have as rigorous of standards to get in, and so it's a lot easier. You just have to have a lot of money to go there, but they give you a U.S. accredited medical degree. And then I lost track of what he's doing now. If he finished, I don't know if he finished or not. Anyway, getting back to this, so can we see in water if it's pure or not? Certainly looks pure to me. But it looks pure, but why the heck do they have this? Did I show you this sign on this thing? Industrial water, do not drink. But man, that looks good. It looks like pure water, refreshing, especially on hot days like yesterday and today. It would be pretty good to drink. But can you see the particulates? You can't see at the particulate level. Do we have something that we can just magnify it and see it? No, because actually we could shine X-rays, but you don't want to be looking at X-rays, number one. And number two, what else about X-rays? Uh-huh.
Yeah, it's want to take a picture of the molecules and stop it from moving for a very long time. It takes a long while to develop the picture.
Yeah, unlike taking a regular photograph with X-rays, there's no. If somebody, this is the difference, and this is not that important, so I understand if you didn't bother registering this in your mind, but there's no lens. Remember, I don't know if anybody remembers. If somebody develops a lens for X-rays, then you can see it real time, like a video camera. You can watch it, although it'd be moving so fast you couldn't really see it with instruments. But this is why you have to freeze it down, and then rather than a lens, you have a detector that detects it, and then you use a computer to regenerate the image of the atoms. But if you have a lens, then you can see the image of the atoms. And so people at UCSB were looking for developing materials that would act as a lens for X-rays, second harmonic generators. But anyway, the point was we can't see at the particulate level. I mean, of course they. What do you mean? Wasn't there the? Remember the? What was that image? Where we could see atoms. What was that image? Didn't they see atoms using a? Using electron microscope or a scanning, what was that? Scanning, tunneling microscope. Didn't they see single atoms? Yeah, so all we have to do is put this water in a scanning, tunneling microscope or an electron microscope, and then we could see the particulates in here, right? No, it's not going to work like that. Why? Huh? Oh, we don't have it? Oh, let's say we had one. We had access to one. Could we see it? Well, one thing is, what would you have to do? Just like X-rays, you would have to cool it down so it doesn't move. And with the scanning tunneling microscopes, the way they operate is you can't just do any old sample. You have to put a coating on the sample, and that coating has to, because it measures it using what we call electrical voltage. It uses, and so it has to build up some kind of charge on the surface. So it's not so easy. In other words, it's very difficult to tell if this is pure or not. And so how do we tell if this is pure or not? That was one of the main points yesterday. Although I didn't spell it out like that, you make that connection later on. Right. For example, if the boiling point of this is at 100 degrees, right? under normal conditions. If you're in Denver, it'd be something else. But if the boiling point were 100 degrees C, then that's good, right? If the boiling point is 101 degrees C, or 103 degrees C, or 80 degrees C, then I wouldn't drink it. Wouldn't drink it. But then it could have a minute amount of impurities. If it has a minute amount of impurities, then the boiling point might not be all that far off. Because what happens is the impurities disrupt or get between the sticky water molecules, cause it to boil higher or lower. Actually, sometimes it causes it to boil higher because a lot of those impurities stick to water even stronger than water sticks to water. And so you saw that sugar water has a much higher boiling point because the sugar molecules stick to water much stronger than water molecules sticking to water molecules, which hinders the boiling of that. But there are other complications to that too, and that is our thermometers that we use are pretty inexpensive thermometers. Our thermometers are, so when we actually do a lab and you see your water's boiling at 99.5 degrees C, I wouldn't worry too much. It could be that the thermometer wasn't well calibrated. It's just reading off a little bit. Okay. But that would be one. Boiling point, I'd check the boiling point. What else would I check? So obviously if the boiling point's not 100, it's not looking good for pure water. What else would you check? This is like the same thing, you know. Let's say a stranger comes up to you and says, okay, I have some gold here. I'm going to give it to you really cheap. And it looks like gold, and you say, oh, that looks pretty homogeneous. It has a golden color, golden luster. I'm going to buy it because you can't pass up a deal like that. Just because it looks homogeneous, is it pure gold? No. And so what do you do? How can you tell? Oh, let me take a moment and go to the scanning tunneling microscope. Gold will work very well on an STM or electron microscope, but I don't have access to one. And so then what do? You start looking at, this is something else we talked about yesterday. You start looking at, what's this called, boiling point called? A physical property. We look at properties because for pure substances, the properties are fixed, right? And for mixtures, the properties are variable. And so fixed, because why are they fixed? Because pure substances have a fixed or variable composition. Pure substances have a fixed composition, right? And so these are all things we talked about yesterday. But you know, the good thing about reviewing it in the manner I'm telling you to review it is that once you have this in your memory, and it's not that hard to get into your memory. Trust me, it just takes a repetition. Once you get it in your memory, then you'll have a much more solid foundation to continue. But the thing is, getting into memory, you have to make sense of it. And making sense of it is a big process. And then sometimes you don't make sense. Later on, something clicks in your brain, and then it organizes all the information and seems to make sense. Okay, so we can do boiling point. What are some other physical properties we might measure? Melting point, we could try to freeze this. It should freeze at, pure water should freeze at 0 degrees C. If this were contaminated, actually the freezing point's a little lower because, what happens is the impurities get in the way of forming that nice blank solid. Crystalline or amorphous solid? Crystalline solid, right? And so that screws up the crystallization process, which means you have to have an even colder temperature. And so we can measure the freezing point. What else could we do? Give me another physical property we can use. Its weight? Well, yeah, we could use its weight, but what we do is we don't call it the weight, because what weighs more? Yeah, you've heard this probably. What weighs more, a pound of feathers or a pound of gold? They weigh the same, so we don't use weight per se. Instead, we use density. Do you guys remember what's more dense, regular Coke or Diet Coke? It's more dense. Did I show that video? No, I didn't show the video? Let me show that video. Regular Coke or Diet Coke, or maybe they have the same density as water. But which one do you think is more dense? I heard regular Coke. Okay. Okay, obviously Coke is not pure water, so it's not going to have the same density.
This is a lovely, simple experiment that you can do when you're working on liquid.
So we can measure its density. That would be an easy way to tell about gold, because gold is very dense. Gold is one of the most dense elements on the periodic table. 1 milliliter of gold, or 1 cubic centimeter of gold, weighs about 20 grams. You know what 1 milliliter of water weighs in comparison? 1 gram. So gold is 20 times more dense than water. And so if you've ever lugged a gallon of water, that's 8 pounds, right? And so a gallon of gold would be 20 times heavier. And so that would be like lugging 1 gallon of water, 8 pounds. Lugging 1 gallon of gold would be like lugging 20 gallons of water. I don't even know if I could pick that up. Could I? Maybe 200 pounds. Less than 200 pounds, maybe. Well, anyway, we could measure the density of water, and so it should be close to 1 gram per milliliter. We can do that. And so the properties are very important. There are other properties too. Smell. You know, if this doesn't smell like water, then something's wrong. Taste. What do you think taste is? Taste is a physical property or a chemical property? Smell and taste, physical property or chemical property? Well, it's tricky, but smell and taste are typically thought of as physical properties, because what happens is there's receptors, and the molecules hit the receptor, but there's no reaction. It's just a sensitivity to a certain type of receptor. Give me a chemical property of water that we might be able to use.
Like the bonds between the atoms and all that.
Okay, the bonds between the atoms, the bonds that hold the hydrogen atoms and the oxygen atoms, how can we test that? How can we use that? I mean, I need to know. It's like the geologist out in the field. I don't have access to sophisticated instruments. You're right, we could test the bonds. You know why? There's an easy way to detect water using sophisticated instruments. And one way of using water to test, and this is how they're looking for water on other planets, is they're measuring what's called the spectrum of the, and so they look at how water interacts with infrared radiation. And if I shine a certain infrared radiation, then there's a big band that occurs for water. Actually, multiple bands that occur for water. And I look for those bands. If I see a band here at this frequency, oh, that's water. You know? And so that's how we can use the bonds, because the bonds are doing what? The bonds are vibrating, and those vibrations correspond to certain resonant frequencies, and those resonant frequencies we can use. So if we had access to instruments, we can detect this really fast. Is it water? Yeah, we can see, but we don't. So what we do typically is we're like the geologists out in the field. We're going to just use what we have. Freezing point, that's easy. Throw it in the freezer. Boiling point, that's easy to try to boil it. Density, that's not hard to measure. We're going to measure that next week. What else? Smell, taste, physical properties. We look at it, it looks homogeneous, it looks like water. If this didn't look like water, I wouldn't drink it, that's for sure. Color is another big one. Color is one of the big ones for geologists. They're very interested in the color, these things. How about chemical properties? Tell me a chemical property. Not of water, but just give me a chemical property that we talked about. Flammable. And so what we could do is we could try to ignite this. If it ignites, then don't drink it. Stay away. All right, so anyway, we talked about properties, physical and chemical properties. What else did we talk about yesterday? Just take a minute and go through your notes and see if we're missing anything. Maybe that was it.
If I'm going to be doing this as my job, why keep us from using that? This is the one class I've been dreading. How long have you been here for? So it's like, yeah. Great classes. Or stopping to tell us. Right, you don't know what's going
Was that pretty much it? Yeah? Not much else? All right, let's go ahead and we're going to finish up chapter 2 today, and then we'll start with the lab. And at the end, we'll do some check-in. And so we have types of pure substances. Both of these pure substances are going to be known for fixed composition and fixed properties. What did I say about the composition and properties for mixtures? Variable. But if you have, some mixtures, if you make it the same each time, then you should expect the same properties. Okay? It's just that, there's difficulty making it the same each time. That's the only thing. So if we look at sterling silver is not pure silver, it's a mixture. And this is a homogeneous mixture. homogeneous mixtures, when we have a homogeneous mixture, we have different names for them. So for example, homogeneous mixtures are often known as solutions. Did I talk about that the other day? I forgot to, but I think solutions, or maybe I forgot to in the morning. But we have solid solutions, liquid solutions, and gaseous solutions. Give me an example of a gaseous solution. Methane is pure. Methane is pure CH4. That would be pure. Air. Something that's related to methane that is a mixture is natural gas. Natural gas is not pure methane. Natural gas is mostly methane with some ethane and a little bit of odorant, because methane and ethane are odorless. Do you know how many carbons methane has? Do you remember the methane molecule? Did anybody write it down? Did I even show that slide? I didn't show that slide. Do you remember seeing this yesterday? Do you remember seeing this or not? Yeah? All right. How many carbons does methane have? 1. Do you know how many carbons ethanol had? I asked you that because it was hard to see in the... It was 2 carbons. That's ethanol. Do you know how many carbons methanol had? I'm sorry? No, it has more than 0. Less than infinite. How many carbons does it have? Has to be an integer. Methanol. Wood alcohol. Remember? You remember wood alcohol? Wood alcohol is coming from this. This is cellulose. Cellulose. Ose. You know that ose ending? These are the things you notice when you go through your notes over and over again, because it gets kind of boring and repetitive. And then you start noticing little patterns, like we talked about sucrose, we talked about glucose, and we talked about cellulose yesterday. And then, you might not see a pattern there initially because it's the first time you heard it. But after the 20th time of looking through your notes, you go, that's interesting. All of them end in ose. And so there's a connection. Yeah, you're right, there is a connection there. That connection is, these are all carbohydrates. So even wood is a carbohydrate, although you can't eat it, but this is it. And wood consists of, or cellulose or paper consists of, what are these called again? I know this is beyond the book. It's beyond the book, but it's not hard to pick up, because let me tell you, how many of my instructors at UCLA followed the book along section by section? Pretty much 0. You had to pay attention to what they were saying, because that's the stuff that was going to be on the test. And so you got to, even though, we didn't talk about this, and if I was evil, I would put it on the test, right? Well, there are plenty of professors at UCLA who aren't so nice. You would think, they aren't like, I don't know. It's kind of like the students have a name for it. It's like, that's a weed out course. Weed out, pluck the weeds out of the class. The weeds are the stragglers. Okay? So pluck the weeds out. And so some of the it's not so nice. Not a lot of people say, at the community college level, most of the teachers are really nice. That's what I found at Santa Barbara City too. And so, you got to be prepared, because yeah, it's not in the book, so, but a lot of people say, it's not in the book, it's not fair. Well, professors, they don't care. And so this is why you want to be prepared, whether it's in the book or not. Because if the professor talked about it, it's fair game for the test. And the people who are going to be at the leading edge of the pack are the ones who, can remember. Well, anyway, they go through it and they saw, oh yeah, the os is related to being a carbohydrate. Sucrose, fructose, glucose, etc. If it has that os end, it's a carbohydrate. Which I didn't talk about at all, but you could make a connection later on. And then these are glucose molecules linked together, and we talked about for that. But when they're linked together like this, it makes methanol. Now, I wrote methanol on the board. Did anybody write it down? Did I write the formula on the board? I did. How many carbons does methanol have? How many carbons did methane have? 1. How many carbons did methanol have? Ethanol had 2. Methanol had 1. Just that difference in 1 carbon makes methanol deadly, ethanol consumable. In fact, antifreeze. Antifreeze used to be ethylene, what was it? They changed the number of carbon atoms in antifreeze because a lot of people were ending up dumping antifreeze into the environment and killing the animals. And so they said, okay, we want to make it a little less lethal. So what they did was they subtracted a carbon or added a carbon. I should know this. They added a carbon. And so it used to be ethylene glycol, now it's propylene glycol. But these are the things you notice when you go through. Again, so I'm repeating myself here. These are the things you notice when you make a connection. I remember seeing methane, 1 carbon. I remember seeing methanol, 1 carbon. So meth has some relationship. There's a pattern there related to 1 carbon. Do you see that? And so so basically, I asked you to do some memorization on Piazza, but I'm going to ask you to start memorizing some more. Meth in organic chemistry means 1 carbon. F means 2 carbons. Prop means 3 carbons. So if there's a little bit of propane in natural gas, which there could be, that's a 3 carbon. If there's ethane in the natural gas, it's 2 carbon. If there's methane, and it's mostly methane, it's 1 carbon. Prop, do you know what comes after prop? Bute. Now, propane and butane are liquids, so it's most likely there wouldn't really be much propane or butane. If you go fill up a barbecue tank full of propane and swirl it around, you'll hear the liquid propane in there. But it's pretty volatile. What does volatile mean? The boiling point's low, therefore it evaporates rapidly. It's volatile. And so, these are very volatile. Propane's still fairly volatile. Butane's a liquid also. People use that in like lighters and that type of thing, torches. Do you know what comes after butane? Bute. We have bute. We have pent. After pent comes hex. Good. After hex comes sept or hept. We call it hept. After hept comes oct. After oct comes, what's 9? 9 is known. So it's kind of like 9. It's known. It's probably the German 9. And so after known comes dec for 10. And so you're going to have to start memorizing these prefixes here. And so we saw a little bit of connection already with some of the prefixes, but we'll do that. And so we're going to keep the memorization to little blocks of memorization. Since I'm talking about memorization, I told you to start with the first 3 rows on Piazza. Somebody asked me about the homework, but there's actually much more than the first 3 rows that you want to memorize on Piazza. You also want to memorize all these. These are found in the supplement. Now, I made an error here. Actually, the bookstore made an error. This is not really 2000. This is the 2017. They just misprinted. They probably used the old cover for this. And so a lot of people have been asking me, is this version okay? This version's fine. This is the latest version. In this latest version, you'll go and you'll see in formulas 1 here. Things that we need to start memorizing. And of course, the first 3 rows we need to memorize of the periodic table. And so you want to start off with that, the first 3 rows, hydrogen, helium, lithium, etc. Then let me add to it. You need to remember the first 4 rows. And so start adding the 4th row. And what do we want to memorize? We want to memorize the name with the correct spelling and the symbol. So 1 or 2 letter symbol for the atom. And then there are some other ones sprinkled around, like gold. What's the symbol for gold? AU. And you go, why? That's a weird symbol for gold, but it comes from Latin. I guess aureum or something like that. And so gold we need to know, platinum, silver, those we would need to know. So, if I wanted to check my purity of sugar, honestly, I'm going to borrow a cup of sugar, but before I use that in my cookies, I want to make sure it's pure. So I'm going to check its melting point. Am I going to be successful? I want to measure the purity of my sugar by melting it and seeing what temperature it melts at. Will I be successful? No, because, I want to measure that physical property, but I got something screwed up. And the thing that's screwed up is that it's going to start to burn before it melts. And burning is a chemical change. And so this is the other thing I wanted somebody to mention from yesterday, but I'll go ahead and mention it. And the thing is, that doesn't mean it's not possible to measure the melting point, because somebody had to do it, right? And so how did they do it? How did they figure out? They did it in a vacuum. That's a great idea. You could do it in a vacuum. If you do it in a vacuum, you could melt it that way. But you don't have to do it in a vacuum, because it's tough to get it in the vacuum and do that. And the vacuum could change the melting point. It's like ice. Do you know the melting point of ice changes depending on how much pressure you apply to the ice? So, for example, if you apply a lot of pressure to the ice, will it melt easier or will it melt harder than normal? It'll melt easier. And therefore, that's how ice skates. When you ice skate, it applies pressure there, and it melts a very thin layer of ice, and then you don't have that much friction, right, in ice skating. But the problem with the vacuum is, if you do it in a vacuum, that could change the melting point of the ice. And so we don't necessarily want to do it in a vacuum, but we need a vacuum. What we could do to melt sugar is get rid of the air. If we don't have any air there, there's no oxygen. If there's no oxygen, it's not going to burn. So how can we get rid of the oxygen? Well, there are different ways to get rid of the oxygen. Maybe we could use somebody remember anything about the molecular? Did I talk about it? Did I talk about the molecular? Sometimes I have deja vu, because I have 2 classes in the morning and in the afternoon. I talk about the same thing, so you got to catch me. I'm doing this to make sure I didn't miss anything myself. But one way is we might try to filter out the oxygen using a molecular sieve. Did I talk about molecular sieves yesterday? Yeah. Okay. Good. So that's one thing we could do. We could try to filter out the oxygen. That is, keep the nitrogen. And nitrogen, you know what they call nitrogen? They called nitrogen a pseudo-Nobel gas. Do you know what the Nobel gases are? The Nobel gases are this last column of the periodic table. This last column of the periodic table, helium, neon, argon, krypton, these are the noble gases. Why do they call them the noble gases? They call them the noble gases because they're very stable. They're very unreactive. They're just happy as is, and they can't really be attacked chemically. And so as far as chemical properties go for the noble gases, there's really not much. Not much. And so nitrogen itself is known as a pseudo-noble gas. Do you think you could burn the sugar under nitrogen? No, we need oxygen, right, to burn the sugar. Now, so that's one thing we can do is maybe we'll just use a molecular sieve and one of those little pumps, $2,300, something like that. Maybe that would work, you know. Or we could just go out and buy a cylinder of nitrogen, do that. But the thing is, this is the way we do it. We put the sugar in a container, a very strong container, and then use a vacuum, suck out all the air. We suck out all the air. Can we suck out 100% of the air? No, it's too difficult to do. So we suck out most of the air, and then we backfill the container with one of these noble gases, neon, argon, krypton, or maybe nitrogen, pure nitrogen. And then we do it over again. And this way we flush out all the oxygen out of that container. Does that make sense? Just repeat, repeat, repeat until we get pretty much inert gas. Inert, do you know what inert means? Unreactive in there. And then we can melt it. We wouldn't have to worry about it charring or caramelizing or burning. We could melt it easily that way. But what a pain, you know, to melt. I'd probably just forego that and just use it as is. But chemists don't normally do that. If chemists are given an ingredient, you check it first. That's the typical protocol. We want to check it first to make sure the ingredient we are using is what it says it is. There's a very famous story that happened at MIT. At MIT, some people just grabbed a bottle of reagent, we call them reagent, grabbed a bottle of chemical off the shelf and started using that. You know, they read the label, oh, this is the stuff I want. And they used it, and they did 5 years worth of work using this bottle of stuff. But the bottle of stuff was totally contaminated, and it wasn't what they were expecting. Somebody had totally, basically they never analyzed it to see if it was pure. Fortunately, it wasn't a complete waste. They just had to redo all their papers. A very famous story. Anyway, these are the noble gases. Nitrogen is a pseudo. You know, in fact, it's very hard to burn nitrogen. How can you burn nitrogen? Will nitrogen burn? You know, okay, I put it in with the sugar and I start heating it up, but maybe the nitrogen's going to burn. Is it possible for nitrogen to burn? Have you ever heard of nitrogen burning? When nitrogen burns, it forms compounds called NOx. Have you heard of NOx? N-O-X? Where did you hear that before? How can you burn nitrogen? Where have you seen NOx before? In car engines have extreme pressures and extreme temperatures, so you can actually burn nitrogen. But when it burns with oxygen to form NOx. NOx are pollutants and smog. But other than that, nitrogen, and this is why we call it pseudo-inert gas, because if you try to do the same thing with neon, forget it, neon's not going to burn, argon's not going to burn, none of those gases will burn. And so it's pseudo-inert. Gold is like the noble gases. You know, gold doesn't really burn at all. You know, gold's very stable. So gold is noble metal. It's not a gas, so we call it noble metal. Platinum is very stable. And so platinum is also a noble metal. How about silver? Is silver very stable? Is silver as stable as gold? If you had a choice, gold jewelry versus silver jewelry, which one would you pick? Gold. Silver jewelry versus copper jewelry, which one would you pick? Silver. That's because of this. You know, gold is a lot less reactive chemically than silver. Silver is a lot less reactive chemically than copper. Now, if we have an alloy like sterling silver, you know, sterling silver, that alloy, let me go back to that, but these are the things you want to memorize here. And start memorizing these. This is in Formulas 1 in your Chemistry 4 supplement. When I look at this looks pretty homogeneous. This looks like pure silver to me, right? But we can do certain things like measure its density, et cetera, and tell if it's pure silver or sterling silver. Sterling silver, is it a compound or a mixture? Sterling silver is silver plus copper or silver plus other metals. Is that a compound or is that a mixture? It's a mixture, right? A compound, well, what's the difference? Why can't I call it a compound? It's a compound of silver plus copper.
Compound can be separated chemically.
Yeah, compounds must be separated chemically. They can't be separated physically. That's one way. Is there another way we can tell that this is... Well, one of the major differences between a compound and mixture has to do with the, like when you buy water, you know, when you buy water, is there a chance that if you buy water from one store, that water has a little bit more oxygen than another store, and so this store has a little bit less oxygen in my water, and therefore I want more oxygen, need to breathe, and so I buy water from this store which has a little bit more oxygen. Is that possible? It's not possible because compounds have a fixed, what? Yeah, based on having a fixed, they have a fixed set of properties because they have a fixed composition. Mixtures will have a fixed set of properties if you make the mixture the same each and every time. If you make the mixture the same every single time, it's like making a cake. Every single time the cake is going to come out the same way because every single time you make it exactly the same way. So mixtures can have a fixed set of properties too. Otherwise we can't make those predictions, right? And so, well, this could be a compound then, because let's say we fix the composition. The composition's fixed at 92.5% silver and 7.5% copper. Isn't that fixed? That's sterling silver, right? But the situation is this is a mixture, because let's say you go to one dealer, one vendor, and they say, okay, I got my 92.5% silver, right? But let's say, okay, you go and have it analyzed. It comes out to 92.46%. 92.46%, you go, hey, it came out to 92.46, not 92.5. And then they say, well, 92.46 rounds to 92.5, meaning you got the right amount of silver. And then you go to another vendor. The other vendor, they made it 92.54%. So 92.54%, hey, that's a little bit more silver. I might as well get it from that vendor because I'm getting a little bit more silver, less copper. And so it depends on who makes it, right? Who made it, and even then the same person can make it, but they make it slightly different each time. They make it slightly different. This is different than water. Can you make water slightly different each time? No, it's not possible. So this is the key difference between now mixtures. We can separate the copper from the silver using physical means, like melt it. This is melt it, and then we can separate it. Something like that. But compounds, we can't do that. And so an example of a compound is this. You know, this silver looks pretty good, but you know, even though silver is considered a Nobel metal, it's a little bit more reactive. And so let's take a look at this. This is pure silver here. If we look at this well, does that look like pure silver? No, at one time this was pure silver. At one time. But what happened to the surface of this? The surface of this got tarnished. We call it, for silver, we call it tarnish. For copper, we call it oxidation, or other metals. It gets oxidized. And so we got this silver tarnish here. Well, I don't like tarnish, and some people don't like tarnished silverware. So what they can do is they get some buffing compound and rub off the tarnish. But if they rub off the tarnish, what are they losing? They're losing some silver. And this is a silver compound, actually, that's on here. And so I don't want to lose any of that silver. So I have a compound, but I need to get the silver from my compound. And so this is what was mentioned. If I want to get the silver from my compound, I can't filter out the tarnish. I can't do any of that. I can't use chromatography. Can't use distillation. I'm going to have to use, if I want the silver and I don't want to lose it, I'm going to have to use a chemical separation technique. And so there are chemical kits that you can buy that you just dip this in. And what that does is it just kind of reverses the process and converts the compound back to elemental silver, so we don't lose any silver here. Of course, this is a very valuable coin, so they probably aren't going to do anything with it. Just leave it in this natural state. These are diamonds here. Even though these are supposed to be pure carbon, the way they interact with light can vary. And some of them have impurities in them. And so I organize it a little differently, and I think about matter differently. I don't think of it from top down here, like they did. In fact, I think of it like this. And so my flow chart's different than the book's flow chart. In fact, I completely ignore this figure. Other figures I pay attention to. And so here we have some elements and compounds, like the lead in the pencil. The lead in the pencil, is that an element or a compound? You know what the lead is made out of? It's not made out of lead, it's made out of graphite. Graphite turns out to be pure carbon, and so that's an element. Carbon can form graphite or diamonds, just pure carbon but different structures. This is silicon, the element silicon. I don't know what that is. Gold? It's hard to tell from the color. This is copper. This is, you know what these look like to me? That's either zinc coated steel or that's stainless steel. Is stainless steel an element, compound, or mixture? It's a mixture. There's lots of different formulations. These are lead weights. That should be an element. This is copper. This might be gold foil on the CD. Very, very thin layer of gold. Over here we have some compounds, baking soda, etc., chalk, water. These are all compounds here. All right, we're going to start learning more about elements and learning more about compounds. So one thing we got to do is start memorizing the symbols and names for the elements, like hydrogen, helium. And sodium here, Na. But certain elements are represented differently. So for example, hydrogen. Hydrogen doesn't like to be alone. Hydrogen likes to pair up with another hydrogen to form H2. There are 7 of these that don't like to be alone. And we call these the diatomic, di for two atom molecules. And so hydrogen's one of them. So if somebody's talking about hydrogen, they're most likely talking about H2. Okay, what else? Oxygen, O2. But before oxygen, nitrogen. Nitrogen's another diatomic. It's very stable. And so the nitrogen in this room that you're breathing right now is N2. It's not doing anything because other than maintaining pressure. But it's not chemically reactive because nitrogen is what we call a not a Nobel because it's not in that last column. It's a pseudo. So it's like silver. It's like silver or copper of the Nobel gases. It's a little bit more reactive than the really Nobel, gases. And so we've got hydrogen, nitrogen, but nitrogen's cheap. When I was in lab, we used to use nitrogen all the time because it was so cheap. We buy from liquid air. In fact, nitrogen's so cheap and so useful, they used to put a gigantic tank. They don't have this anymore, but we used to have a 2-story tank of nitrogen sitting in the parking lot at UCSB. And it was filled not with nitrogen gas, it was filled with liquid nitrogen. And so there was a lot of nitrogen in that tank. So nitrogen and then oxygen, O2, and then what else? Okay, not fluoride, but fluorine. Fluoride is related, of course, but for the element, we'll say fluorine, and then chlorine, bromine, and iodine. These are the 7 diatomic elements. But it's very tricky because if somebody's talking about oxygen, if somebody's talking about oxygen, what are they talking about? We have to be very careful here because oxygen has different forms. Have you heard of O3? O3 is pure oxygen. But what is O3? O3 is called ozone. Ozone is not very happy. It's not very stable. You wouldn't call it a Nobel gas because it's very reactive. It's very unhappy. What happens with the ozone is it breaks apart into O2 and this species, O. O's don't like to be alone. And so if you're in a room full of O, just oxygen atoms, you're going to feel it because it's going to start attacking your skin, your eyes, your mucous membranes. It's going to start to sting. You'll feel it. This is called atomic oxygen. Atomic oxygen is not like any Nobel gas. This is a very reactive gas. So it's unstable. So when somebody's talking about oxygen, we have to be careful because these are called allotropes. It's like graphite. If somebody says, okay, I need some carbon, then you got to ask, okay, what kind of carbon do you want? Do you want diamond? Or do you want graphite? Or do you want charcoal or amorphous? Charcoal is mostly amorphous carbon. You have to, and so these are called allotropes. Allotropes are different forms, in other words, different structures of the same element. So let me ask you this. If somebody's talking about oxygen, carbohydrates have carbon, hydrogen, and oxygen. Alcohols have carbon, hydrogen, and oxygen. So if somebody's asking about, okay, how much oxygen is in ethanol, right? What are they talking about? Are they talking about O2, O3, or O? What do you think they're talking about? I'm curious how much oxygen is in ethanol. Are they asking about O2, O3, or O? Or how much oxygen is in cellulose? Let's do that because I already have that figured out. Let me cellulose up here. Let's say, you know what? Let's say I am trapped underwater and there's this old piece of wood there, sunk, waterlogged. Can I go to that old piece of wood and suck the oxygen out of the wood so I can breathe underwater? Is that possible? No, because the oxygen in wood, do you see any O2 in the wood cellulose here? No. We're talking about atomic oxygen, atoms of oxygen. And these atoms of oxygen are linked. For example, here, you don't see it, but this is carbon, oxygen, carbon, that link there. And this is a carbon, oxygen, hydrogen link here, or bond there. So there's no O2 in here. Whereas if somebody said, I need some, how much oxygen is in air, then what are they talking about? Are they talking about atomic oxygen? No, because if this room were filled with atomic oxygen, you'd be miserable right now. It would be O2. You know, I mean, in fact, people buy bottled O2 to get, you know, a little refresh or recharge. But you wouldn't be buying a bottle of ozone. And a bottle of ozone wouldn't last very long. And the same thing with atomic oxygen, because both of these are very stable. These aren't noble at all. They're stable. These are very unstable. The opposite of noble. In that way, in that sense. Well, I'm going to just finish up really quick here. We're going to learn about compounds, all different kinds of compounds. Compounds like HCl. HCl is called hydrogen chloride or hydrochloric acid when it's mixed with water. H2O, water. BaCl2, which is barium chloride. This is called barium chloride, but do you know another name for water? You know, one day I was looking for ammonia. I couldn't find ammonia in the catalog. Yeah. A lot of people call water dihydrogen monoxide. In fact, there are some pranksters. Did you hear about this? There are some pranksters. There's a city in Northern California. The city in Northern California started banning certain chemicals from city services. You know, they didn't want to use these chemicals because these chemicals were harmful. And so a group of pranksters petitioned the city to ban dihydrogen monoxide. The reason is because dihydrogen monoxide is potentially toxic. You know, if you drown, you could die. And so the city came up with a resolution banning dihydrogen, and it was serious. Can you believe that? They seriously banned dihydrogen monoxide, or made some kind of resolution banning dihydrogen monoxide. I don't know if it's true, but that's what I heard. And if you look at it on Wikipedia, you can see the details of it. But the story I was told was slightly different than the Wikipedia version. But it's funny. It was funny. Dihydrogen monoxide. Well, why didn't we call barium dichloride? And there's reasons for that, and we'll talk about that later. And we talked about atoms and molecules already, so this slide's already done. We have atoms, molecules, and what else? Now, along this line, atoms, molecules, and lattices. And for lattices, we had two types, but the two types of lattices don't worry about now, but you know, you just it's one of the questions that are changing. You heard of the law of constant composition? The law of constant composition is given different names. Another name, give me another name for law of constant composition. Maybe I didn't mention it. It's also called the law of multiple proportions. Can you tell me what the law of multiple proportions is? We talked about it yesterday. Uh-huh. Yeah, that's good. That's good. Where did the law of constant composition or law of multiple proportions come from? Yeah, Dalton's. It came from Dalton, not just Dalton, but Dalton. The theory lives on. The person might have passed. Comes from atomic theory. That's where it came from. So this is all kind of review from yesterday. These are the types of things hopefully you have in your notes, you know. Because again, we're at the beginning of the marathon. As the marathon progresses, you know, where do you want to be? Where do you picture yourself? And you can easily be in the lead pack. You don't have to be totally physically fit or whatever else. All it takes is a little bit of effort, and it's not that much effort that it takes to read 10 pages of notes, or I don't know how many pages you have, 20 pages of notes. How long does that take? A couple of minutes? 5 minutes, maybe less. Anyway, let's go on here. Electrical character of matter. I talked about this earlier, that, you know, the stickiness of water. Remember I was talking about the stickiness of water molecules? That stickiness comes from electrical interactions. And when we think about it, things that are sticky to one another are things that are opposite in charge. We have positive charge, we have negative charge, and we have neutral. And so the rule for this is that unlike charges stick together. Unlike charges attract, like charges repel. So unlike charges attract, like charges repel. So these balls are representative of the water. Water molecules like to do this. Do you see these balls are stuck together? They're stuck together because these balls are oppositely charged. You know, what they did was they generated static electricity on this rod here. This is a silk cloth generating some static electricity. And now they are going to charge the balls the same charge. When they charge the balls the same charge, that is positive, look, do the balls stick together? No, they repel one another. And so this is like charges repel, unlike charges attract. Okay, now they're going to reverse it. They're going to rub the plastic this time with fur and then create a negative charge and just charge one of them. So they charge one of them, the left one, and take a look, they stick together again. And so this is what's happening with water molecules. They stick together because of these electrical attractions. Not only that, the hydrogens and the oxygens, you know, they're bonded together because of very strong electrical attractions. Very, very strong. Like 20 times stronger, you know, than these type. Yeah. So electrical attractions are very important. But we also talked about, you know, we talked about, what were the forces we talked about? Does anybody remember the forces that we talked about? I'll tell you one, gravitational force. What was another force we talked about? Or maybe we didn't. You got to remind me. Electrical force. And then there's one more. Has to do with radioactive. Radioactive. Nuclear force. Nuclear force, nuclear chemists are interested in nuclear force. We're interested in electrical because all the chemistry, analytical, organic, biochem, all the chemistry is dealing with electrical forces. This is the foundation, this is the basis for chemistry, electrical forces. All right, here's some what we call chemical equations. Chemical on the left are the products or the reactants on the left. Reactants. On the right is the product. So what we do is we take this, this is burning some coal, charcoal. Charcoal is amorphous carbon. It's very hard to burn graphite. Have you ever tried to burn graphite? Extremely hard to burn graphite. Have you ever tried to burn diamonds? Yeah, burning diamonds is like trying to burn graphite. It's very hard. But charcoal is, the amorphous isn't so hard to burn. It's still tough to burn, but this is just burning charcoal to form CO2. Here's an example of a, going forward here, this is a reaction. If we go backwards, what we're doing is we have to use a chemical reaction to separate the carbon from the oxygen. And we can do that with CO2. Well, for water, we can't separate the hydrogen from the oxygen using a filter or anything like that. In order to separate the hydrogen from oxygen, we have to use what type of separation? Chemical or physical separation? Chemical separation. That's the only way we can do that. And chemical separation isn't that hard. We have a technique called electrolysis, which would do it without too much difficulty. Electrolysis. And this is why, did I tell you about the hydrogen cars, you know? On 190th Street over here, there's a hydrogen filling station. Have you seen it? Yeah. And then I think on Prairie, there's another hydrogen filling station. And so I was thinking, hydrogen, why do you want hydrogen in your car, you know? Because I wouldn't. Initially, I wouldn't. So I talked to this guy. I met this guy. He has a hydrogen fuel cell car. He's driving around. This is a little Mercedes one. And I asked him, don't you feel uncomfortable? Because, you know, having hydrogen under your car is very uncomfortable because it's potentially explosive, right? If you think back, have you ever seen the Hindenburg, the video from that? You know, you're thinking you're driving along, somebody hits you, and you go up in a huge fireball. Is that the way you want to You want to go? Yeah, so I thought, no, there's no way. At least gasoline, you have a little bit of time to run away, right? But with a compressed gas, it's a whole different story. When you have a compressed gas, like compressed air, if I had compressed air and the top got knocked off, and let's say I had a bottle at 2,000 psi, that gas would leak out of that so fast, it would purge the air out of this room. And so one of the things that I did was, if I'm working with compressed nitrogen, you have to be careful, because if that nitrogen cylinder tips over, the valve breaks off, you could asphyxiate yourself, because the entire lab would be filled with nitrogen in no time, like 1 second, boom. So much nitrogen gets leaked out of that tank and pushes all the air out of the room. And then you're just breathing pure nitrogen with no air, no oxygen. You're going to die, right? And you don't have that much time to escape because it's compressed gas, right? Whereas gasoline's a liquid, and so you have some time to escape. Maybe not. It all depends. But with hydrogen at 2,000, actually it's more than 2,000 psi. I looked at it on the website. I think Mercedes website. It was more like 6,000 psi or 20,000 psi. I can't remember. But that is huge. And that would result in a gigantic fireball. Like you read about the methane explosions leveling an apartment building in New York. Or not leveling, but destroying an apartment building in New York. Did you hear about that one? It happened, a natural gas leak in New York. Destroyed an apartment building. It was like last year. No. Well, think about hydrogen. Yeah, that would be something. You get in a car accident, it levels the entire block. This is this gigantic hydrogen fireball. But he said no, he doesn't feel uncomfortable at all. This guy's a chemist too, and he said he no problems, because before he got it, he watched a promo video where they took one of the tanks that they use for the car up to 60,000 feet and dropped it into the desert floor. And when it hit, they went to examine the tank, no damage, from 60,000 feet. So after that, he thought, it's safe. There's enough safety valves in there that he's not worried at all about that happening, right? But that brings up this. How do you generate hydrogen? You can generate hydrogen from water, by chemical means. It costs money though, because you need electricity to do that. And then you could use that hydrogen to power your car. This is 4 carbons. What's 4 carbons? Methane's 1 carbon. What's 4 carbons? Butane. So this is butane, a burning butane. You burn butane, what are you going to get? You're going to get energy. Now, when we talk about energy, we talk about what type of energy have we talked about so far? We talked about kinetic energy, right? Kinetic energy is energy of motion. But there's another type of energy that's involved. What would you rather have in the trunk of your car? A tank of air, like you're a diver or something, or a tank of hydrogen, like you're a chemist or something? What would you rather have in the trunk of your car? Or does it matter? Let me tell you that. They're both at the same kinetic energy. The tank of hydrogen is at room temperature, let's say. The tank of air is at room temperature. And so the hydrogen and the air have the same energy. One's not hotter than the other. The hydrogen tank is not hot. The hydrogen tank is just cool at room temperature. And so somebody might say, hey, I got a couple of tanks here. Don't worry. They both have the same kinetic energy. Can you store these in your garage for me? And one tank is hydrogen, the other tank is air. Would you feel comfortable storing those in your garage? No. Because you probably end up reading a story about the house exploding and leveling the entire block. But the reason is it's not because of kinetic energy. The reason is it's because of another type of energy we have to worry about. What is that other type of energy? The other type of energy is this. Do you have to worry about the air potentially exploding into a big fireball? Will air potentially explode into a big fire? No, if there's no fuel around, it won't. But the hydrogen, would you have to worry about the hydrogen exploding into pure potentially exploding? Not, doesn't have to. Yes, you do. And so in addition to kinetic energy, we also worry about something else. It's potential energy. And this is it. When I think about this, I talked about, the laws of thermodynamics. How solid are the laws of thermodynamics? Would you say there's some violations of the law, but for the most part, very few violations of the laws of thermodynamics? Do you recall what I said about the laws of thermodynamics?
There is no exception.
No exceptions. In fact, people have been trying to find exceptions for how many years? People have been trying to find exceptions for hundreds of years now, but nobody's found any exceptions. The first law of thermodynamics is this: law of conservation of energy. Quantity of energy within an isolated system does not change. Well, what does that mean? That means that energy is neither created nor destroyed. Energy is neither created, it's like atoms. Atoms are neither created nor destroyed, unless we're talking about nuclear. But we aren't talking about nuclear, because nuclear deals with nuclear forces. Nuclear forces is the realm of nuclear chemists. And we aren't working with a whole bunch of radioactive species. So, energy is neither created nor destroyed, just like atoms. It's just changed around. And so this is what we have when we analyze this reaction back here. What we have is this. If I have butane mixed with oxygen, that's a mixture. Let's say that mixture is at room temperature, so it's got some kinetic energy. Then I have a mixture of CO2 and water. That's also a mixture. CO2 and water is a mixture. It's at room temperature, so it has some kinetic energy. If the butane and oxygen is at the same temperature as the CO2 and water, then they have the same kinetic energy. Even though they have the same kinetic energy, they have different potential energy. So what would you rather store in the trunk of your car? A tank of butane and a tank of oxygen, or a tank of CO2 and a jug of water? What would be less potentially explosive as far as a mixture goes? CO2 and water is a lot less explosive. And so what we say is CO2 and water has a lower potential energy than butane and oxygen. Butane and oxygen has a high potential energy because there's a high potential for fire or explosion. Does that make sense? And so, so what we have here is this. If this is, even though the kinetic energy is the same, the potential energy is different. This one has high energy, this one has low energy. So if we're going from high energy to lower energy, energy doesn't disappear like phlogiston. Remember about phlogiston? It doesn't disappear like phlogiston. Energy is going to be there. And so what's going to happen is, that energy's got to go somewhere, and then energy leaks out. And this is why we get the flame, all that energy, the change in potential energy. And so this is the energy leaks out here. It's potential energy, though, not kinetic energy. What is potential energy? Potential energy is the energy due to the arrangement of the charged particles in a system. These definitions aren't very good. Potential energy is, is it potentially very reactive or is it very stable? I'm looking at, is it like a Nobel gas or is it like a crazy oxygen atom trying to attack everything, including your eyes, and it's like. And so that's what I'm talking about in terms of potential energy. Is it stable and mellow, or is it crazy and wild, like ozone? That's potential energy. And so look at the mixture here, CO2 and water. Is it CO2 and water stable, mellow, or crazy and reactive? Stable and mellow, CO2 and water. How about, what's this, C6H12O6? Glucose. Sugar and O2. Sugar and O2. Have you heard of the explosions at the candy factories? Have you ever heard of an explosion at the candy factory or bakery? They happen all the time, especially the bakeries that use powdered sugar. The bakeries that use powdered sugar, or the factories that use powdered sugar, the powdered sugar gets fluffed up into the air and forms an aerosol. And somebody has a match, and they light the match, and you get a big rapid flash fire. It's a rapid flash fire because you got all these tiny sugar particles and catching on fire. It's just going to have a big flash. Have you ever heard of that? Have you ever heard of a grain silo explosion? No? Oh, maybe I'll have to show that sometime. But which one has a higher... Now, kinetically, they could be at the same temperature, so kinetic, there's no difference, let's say. But which one has a higher potential energy? The right side or the left side? A higher potential energy. The right side. Therefore, in order to get this reaction to go, we need to input energy. Otherwise, we can't go up there. And so that's potential energy. In order to understand energy, we need to know the total energy. The total energy is you'll learn this in physics. The total energy is the sum of the potential energy plus the kinetic energy. That's the total energy. And so far we've only been looking at kinetic energy, but potential energy is very important too. And energy is conserved just like matter is conserved. This is kind of more of the realm when we get into nuclear chemistry. So I'm not really going to talk about the relationship between mass. Mass is matter and energy. Mass and energy can be interconverted using Einstein's equation here. And so we have to modify these laws. Remember I said there's no violations of laws? Well, they found a violation of the law. They found the violation of the law in both. In terms of matter, and it was a very, very small violation, and it wasn't even, you can't even measure it, the violation. The only reason they figured it out, that there was a slight deviation from the law, was because of nuclear reactions. They could see it much more in nuclear reactions than in chemical reactions. And so the law was modified. If we do the law of conservation of mass and energy, then there's no violation. Okay. If we just leave it as the law of conservation of mass or the law of conservation of energy, then there's a slight violation. But it's still a valid law because, of how we use it. And essentially, there's no violation. All right? And so let's not worry about that yet. When we get to nuclear chem, then we'll talk more about it. But what we need to know is about this kind of stuff. So this is the end of the step. This is talking about conservation of energy here. You could read about it if you want, but I'm going to stop here, and then what we're going to do is we'll take a break for 10 minutes, and then we'll start the lab. The lab's pretty short, so it won't take us very long to run through it. Okay?